Okay, we're going to start chapter 5, which is the chapter that deals with gases. But before I do that, I wanted to show you something. This is just a teaser, quick little teaser. Purely math, but I'll tell you where we're going to see this again, which is take a look at basically a math function, so simple, an n squared, where n is some integer starting with 1. Then what you can do is you can draw for every value of n is 1, n squared is 1. If n is 2, then n squared, of course, is 4, but we can draw that as 1 plus 3. If n is 3, then n squared is 9, 1 plus 3 plus 5, etc. Look at this pattern here. Basically, it shows that for integers, n squared is essentially a sum of the odd integers starting at 1. Okay, well, I don't know, maybe that isn't terribly interesting, but if you think back at our orbital discussion the other day, you remember that in the first series, hydrogen had just one orbital, basically the s, and then as you move down, we had the s and the p had 3 orbitals, and then once we got down to the transition metals, we actually had 5 additional orbitals, and then finally, to include those inner elements, we actually had 7. Well, it turns out all of that is tied to some math that was done as part of quantum mechanics relating to n squared. So we'll come back to that when we get to chapter 7 and 8. But I thought that was kind of interesting to pass on to you. Okay, on to gases. So chapter 5 deals with gases, and I had said this before, I think in one of my videos, and certainly when I was talking to you, that in terms of the 3 common states of matter, gas, liquid, and solid, by far gases are the simplest. They're the easiest to deal with, and they're the least complicated. The solids are complex because you get down to at the molecular level, kind of how solids or how the nuclei line up to form certain lattices and all that. In liquids, it's tricky because there's an awful lot of interaction between molecules of the same type in a liquid, because they even though they're not as rigid as they are in solids, they're still kind of heavily co-located. They're very close to each other. But in the case of gases, we're talking about largely empty space, and basically kind of some of the assumptions that you make in dealing with gases assume that the actual molecules themselves are much smaller than the space that they're in. And so from that standpoint, you can almost ignore the volume taken up by the molecules themselves. And that there's so much empty space that these gaseous molecules are just sort of flying through empty space, and they don't really see anything else really until they collide with the side of the vessel that they're in, if they are indeed enclosed in a vessel. And so this is kind of the ideal picture of what it's like to exist as a gas. So I want to start by, and I've got kind of some subjects I want to cover here off to the right here, I want to start with this first one, which is kind of the notion of pressure, volume, and temperature, because these are 3 measurable quantities that factor in pretty heavily when we talk about gases. Okay. So volume is probably the simplest. A volume of a gas is essentially however much room you have to hold the gas if it's enclosed. Okay. So in the case of a nice little square jug like I have here, you can measure the volume very easily, and because it's essentially the total volume that is what we think of as empty space inside that vessel. Okay. So usually volume measurements are the easiest to make with respect to gases. Okay. Pressure is probably the second easiest to understand, because we define pressure essentially as a force, like a weight, if you will, divided by how much surface area the force is applied to. Okay. So if you had there's my volume. I'm going to turn my volume into a weight now. If we had a weight, let's say this is a 1,000-pound weight, okay, and we put the weight on I don't know, let's call it a platform that looks like this, okay, and we put the weight on that platform. The pressure that's applied to this platform can be calculated as the total force, 1,000 pounds, divided by how much surface the weight is applied to. Okay, and so if that surface was, let's say, 100 square feet, then the pressure would end up being 1,000 pounds divided by 100 square feet, and it ended up being 10 pounds per square foot. Okay. And as you probably know or may have heard, a lot of times we refer to pressure using units of pounds per square inch. But this is pretty similar, and I won't bother doing the math to convert this to pounds per square inch. So the point I want to make is, if this 1,000-pound weight, instead of it being on a big platform, like I had indicated, if the platform instead were my toe, for example. I'm not going to kind of draw my toe. Imagine, well, maybe I will try. Here's my big toe, and and this 1,000-pound weight came crashing down on my big toe. My big toe is instead of 100 square feet is maybe 0.1 square feet. That's the size of this toe. So now the pressure that's applied to my toe would end up being 1,000 pounds divided by 0.1 square feet, and that would end up being 10,000 pounds per square foot. Basically 1,000 times more pressure than that when we had that big platform there. So anyway, I just kind of want to put that in perspective, because pressure, when it comes to a gas, is talking about essentially the force applied to by molecules of that gas applied to the small little target that these particles are hitting, meaning like the side of a vessel. Okay, so that's pressure. What's temperature, though? Temperature is the most mysterious of the three. And the book gets into it a little bit when it talks about the kinetic theory, or the kinetic molecular theory, is what it's called. And essentially what it's talking about is that temperature is kind of a measurement of how fast the particles, how much kinetic energy the particles have that you're talking about. And this applies to all phases, solids, liquids, and gases. But with respect to gases, temperature usually translates directly to how much energy, how much momentum, how much kinetic energy the gas particles have. And essentially, as the gas gets hotter, the particles actually have more speed, more kinetic energy, and therefore the particles, when they have more speed, when they strike the sides of the vessel, they create more pressure on that vessel. So essentially, this is kind of a lead-in to essentially say that volume and temperature and pressure all have some sort of a mathematical relationship to each other when it comes to gases. And essentially, they all kind of work in ways you'd expect. If you start with a certain amount of gas and you reduce the volume of that gas, it's going to create more pressure, because the actual the gases, the gas particles that are floating around are striking a much smaller area, similar to the difference between my platform and the big toe. Similarly, when you heat a gas in the same volume, the particles move faster, and therefore when they strike the sides of the vessel, they create more pressure. They actually exert more force against the sides of the walls, therefore the pressure goes up. And essentially all those relationships, including if you start with a certain amount of gas and then you put in another, twice as much, you put in another chunk of gas, so that now you have twice as much gas. There's more particles floating around. Even if you keep it at the same temperature, there's double the number of particles, so when they strike the walls, they're creating twice as much pressure. And so this is essentially the reason why the ideal gas law plays in. And I'm going to come to that in the next video. So I'm going to end this one now, and we'll pick back up on the ideal gas law and some of the other topics in the second one.